Hello, my name is Pushpendra Kumar from India, and I am going to present my paper entitled Power Consumption Modeling of a System of Systems Applied to the Platoon of Vehicles. So I start with the introduction, and we have seen a trend towards complex systems, which are basically integrated system working cooperatively to achieve a common goal. And the advancement in ICT made it reality to deal with such large-scale systems. And such large-scale systems are called system of systems. In 1998, Meyer introduced 5 properties to characterize a system of systems, including operational and managerial independence, emergent behavior, geographical dispersion, and evolutionary development in a system of systems. So now we define this system of system. The term of in this system of system represent the integration, and this integration of systems represent an organization, a federation, or a set of different component systems. And these component system may be engineering system, medicine system, military, economy, etc. But in this work, we focus on engineering mechatronic systems. So when these component systems are networked together through communication to achieve the common mission of the global system of systems. If we look at the state of art, the concept of system of system was introduced in early 90s. The concept one by Einstein, he represented a system of system as a network of many independent systems which are geographically dispersed actually. In 1998, Meyer focused on the operational and managerial independence of these independent component systems. SoS and Kupon in 2001, he described a system of system as a system which is following majority of the properties from the operational and managerial independence, evolutionary development, emergent behavior. So most of the properties should be followed by a system of system. In 2009, Jamshidi compiled many available definitions of system of system and defined a system of system as a complex integrated system which is having heterogeneous component system which are exchanging information in order to achieve the global mission of a system of system. As far as application of system is concerned, they have in transportation, maritime, robotics, biology, sociology, military, and so on. But when we talk about the design of system, specifically modeling, very few contribution is available. Like agent-based model is available, set theory, game theory, hypergraph, but all these models represent the organizational model of a system of system. But to design a system of system efficiently, we need their dynamic behavioral model as well. In 2004, Kumar and allies used this bond graph technique to model the organizational and behavioral model of a system of system. So in this work, we extend this approach of using bond graph to model the power consumption in a system of systems. So the main contribution is, first of all, we present hierarchically a system of system at various levels. Then using the bond graph, a power consumption model of system is developed. The developed algorithm is applied to a platoon of autonomous vehicle, where using this energy-based bond graph dynamic model of vehicles, power is estimated in whole platoon of vehicle and which is analyzed through some simulation results. So it is a hierarchical multi-level representation of a system of systems. Here we have one set of component systems. So basically, if you look, there are Z number of levels in system of system, and this number of level depend on the complexity of a SoS. So here in the first set, we have, this is the first set 1, which is having n number of component system, which are physical component system. And their organization represent a component system CS1, 2 at the level 2. So the second subscript represent the level. So at the level 1, all are represented by 1, and at the level 2, all are represented by level 2. While the first subscript represent the component system number. So here we have n number of component system. In this set, we have m number of component system. So the organization of the first set is represented by CS12 mission, which is having a mission. And the mission of the second set having m component systems is represented by CS12. And at the highest level, we can realize the whole system of system. So here we can see that these are physical component system, but they are only exchanging information between them. But they can operate independent to each other. Only they exchange information. To model this physical component system, we use a graphical modeling approach, bond graph, which is based on the energy exchange between systems. For example, we have two systems, system S1 and system S2. And these systems are heterogeneous. One can be mechanical, electrical, thermal, and so on. The power exchange between these two systems is represented by a power bond, which is represented by this half-headed arrow. And this arrow takes two power variable, effort and flow. And their multiplication in the bond gives the power. The direction of effort and is given by putting a vertical stroke on the bond. So it will be the direction of effort, and in the opposite direction, we will have flow. Similarly, when we put a stroke on the tail, this will be the direction of effort, and in the opposite direction, we will have flow. For example, the dynamics of this system S1 is represented by some inertial element of bond graph, and it is a unified element. It can be a mechanical mass, it can be electrical inductance, and so on. So this inertial element takes effort and integrate that effort and gives us back flow. So this flow is basically integration of this effort, and this is the parameter, the inertial element 1 upon I. Similarly, a capacitive element, which can be a mechanical spring or it can be a capacitance in electrical domain, it takes flow and gives back effort. And this effort will be the integration of flow and this capacitive element. The power in the system can be estimated, which will be a function of effort and flow. Now, we apply this approach to a platoon of autonomous vehicles. So here we define three levels: submicroscopic, microscopic, and macroscopic. At submicroscopic level, we have n number of vehicles, say vehicle 1, vehicle 2, vehicle n. Okay, they are not physically attached, they just exchange information between them. At the microscopic level, we model this information exchange between this vehicle as a vehicle-to-vehicle communication. And finally, whole platoon of vehicle is realized at the highest macroscopic level, where this communication model as well as this physical dynamic model of autonomous vehicles are combined. So we start with modeling of a physical autonomous vehicle at the submicroscopic level. Then we will model the communication. So here we can see that this is a autonomous vehicle called Robocar. And this Robocar is driven by 4 DC motors, independent DC motor, and there are 2 steering systems for front as well as for the rear steering. This is the schematic diagram. Here, this I frame is the earth fixed frame, and this frame, small x and y, is attached to the center of mass of the vehicle. Now, the wheel forces, this is the longitudinal force, and this is the lateral force, and their component along x and y axis, fx and fy, are calculated. Delta represent the steering angle. So here in the bone graph model, we can see this is the model of a wheel, which is powered by a electric motor. So we give the input voltage to the motor, and some energy is lost in the inductance of motor, some is in the resistance of motor, and remaining energy goes further in the mechanical part, where we have wheel inertia, some loss of energy in the viscous friction, and remaining energy goes further. Here, this is the steering model. Delta represents the steering of vehicle. And finally, these wheel forces, Fy in lateral direction, Fx in longitudinal direction, are transmitted to body. So here, from the different wheel dynamics of wheel 1, 2, 3, 4, all these wheel forces, say Fx1 from the wheel 1 and Fy1 from wheel 1, goes to the center of mass dynamics, where we have longitudinal dynamics, lateral dynamics, and the yaw dynamics. So here we have some assumptions that because this is an indoor vehicle, so the terrain is known. So vertical dynamics is ignored because it will be moving. It is assumed that on a flat surface. So now we model the communication between vehicles at the microscopic level. Suppose we have this bone graph model, which we have already developed in the previous slide, of leader vehicle, and bone graph model of the bone graph dynamic model of the follower vehicle. So here it is a communication model between these two vehicles. So basically it takes, here we see that this bond is a full headed arrow, which represent the information exchange in the bone graph. So it will ensure that these two vehicles are not physically attached. It takes the information of flow from the leader vehicle, and the effort will be 0 here. And this flow information is compared. This flow is basically velocity of leader vehicle, and F1 is velocity of follower vehicle. The relative velocity between these two vehicles is F3. This F3 will be multiplied with this Bn. So this Bn is a dashpot coefficient. So basically we model this a virtual connection between these two vehicles. This is a virtual connection for the communication purpose. There is no physical connection. So this virtual connection we model using a spring dashpot system between these two vehicles. So the dashpot coefficient is B1 and spring stiffness is Kn. Okay, so this connection will work as a PI controller actually. So this relative velocity here, this Bn will be multiplied with this dashpot coefficient. So it will be our Kp, proportional control. And here this velocity, relative velocity, will be integrated and multiplied with this Kn. So it will be basically a Ki, integral control. So it will be a PI controller, which will ensure that this difference in velocity between F2 and F1 will be 0, so that they can maintain a safer interdistance. So finally, at the macroscopic level, we combine both the physical dynamic model at submicroscopic level, and communication model at microscopic level. And from that whole system of system model, we can estimate the power in whole platoon of vehicles. Now, simulation result. For simulation, we have used a dedicated software for bone graph modeling and simulation called Symbols. In Symbols, once you draw the bone graph model of the system, its dynamic equations are generated automatically, and those can be used for further simulation. So here we can see some simulation results. This is the position of vehicle 1, black line, and position of vehicle 2 and vehicle 3, which are increasing. So we can see this vehicle 1 is moving with the steady state value around 6 meters per second. And the follower vehicle, say vehicle 2, it fluctuates its velocity to meet with this velocity, also the vehicle 3. We can see when the interdistance is very less between the vehicles. So here we can see around 10 seconds, there is interdistance is reducing. So to maintain increased interdistance, the follower vehicle, say red vehicle at 10 seconds, it starts to reduce its velocity. And when there is a sufficient interdistance between vehicle, it again starts to increase the velocity. So basically it is a stick slip motion. So when there is less interdistance, it will apply brake in order to maintain a safer interdistance. In this curve, we can see the power consumption in 3 vehicles. And here we can see the energy consumption of the 3 vehicles. We see that the energy consumption in the leader vehicle is very less compared to other because of its smooth velocity, while the vehicle follower vehicle 2 and vehicle 3, they are fluctuating velocity, so their energy consumption is higher. Here we can see the initially we kept the interdistance between vehicle 2 and 3 10 meter, and between vehicle 1 and 2 15 meter. So here this interdistance fluctuate, but it converges. As we see, the results are converging. So it tries to maintain this imposed interdistance. Here we can see the power consumption in second vehicle and that interdistance between the vehicle 1 and 2. So as we know that interdistance between vehicle and vehicle 2 is imposed 15 meter. So when this interdistance is less than 15 meter, the vehicle applies brake, and this is the power consumption in the braking of vehicle. When interdistance is more than 15, so it again starts to accelerate, and this power consumption represent the power in acceleration. So conclusion of this work, that power consumption estimation is important to manage the power in whole system of system. And a hierarchical dynamic model is developed for a system of system, which can be used for the global power consumption estimation. And this developed algorithm we applied to a platoon of vehicle, which represents to an organization of system, because these autonomous vehicles are not physically attached. They only exchange information. And because they are autonomous, they show the adaptive behavior and evolutionary behavior by reconfiguration of their structure in the platoon. The developed model is simulated to estimate power consumption of 3 autonomous vehicles cooperating in system of system to complete the task of leader follower car following model. And the obtained result supports the effectiveness of the developed model, which show a safer interdistance between leader follower vehicle. So in this case, we can maintain the whole mission of system to maintain a safer interdistance between vehicle. Also, we can estimate the power consumption in whole system of system. Also, for future work, it is interesting that we can use the power consumption of different component system in order to see the effect of a faulty component system on the performance of the whole system of system. And as we know, that theory of fault diagnosis is well developed in bond graph. It can be applied for the purpose of power estimation in case of faulty component systems. Thank you. And all questions are welcome. Thank you very much.